Okay, this video is really going to be just for the short term here, and I don't plan on leaving it posted because it's going to be kind of a quick and sloppy video. I already tried to make it once and realized I left a couple of things out, so we're going to redo it real quickly here. Question number 5 is a question about power. We haven't done an example of power while I've been in class with you, so we'll do this one really quick. It's probably more complicated than a straight out power question, but here we go. So a couple of quick things since I haven't had a chance to lecture with you. Power is not an amount, it's going to be a rate. It's going to be the amount of energy per unit of time. So it's going to be a rate as to how fast energy gets used. So for example, a large power engine uses a lot of power in a very short amount of time. It's like a Corvette versus a Corolla. So we could also say that's work, although I like to use work as a verb. And energy or work is measured in joules, and our unit of time is going to be the second. All right, so power is measured in joules per second, and instead of saying joules per second, we've given it another name. That is a watt. All right, now we're familiar with the power of a light bulb in watts. For cars, we usually talk horsepower in engines. So one quick conversion factor here is that 1 horsepower is 746 watts. So I already have the problem solved. We're just going to flip it around and walk through it. So here's my car. I have a formula for work that's force times distance, but we don't have a force and we don't have a distance here, so we're going to do this a different way. We're going to start with the initial velocity and the final velocity, and we're going to convert those to meters per second because almost never do we use hours in any of our units. It's always meters and seconds. So a conversion factor for that is to do 1 hour over 3,600 seconds and 1,000 meters per kilometer. If you do that, you'll find it's going to be 0.27777. And this conversion factor is what we use every single time. So just remember that anytime you want to go from kilometers per hour to meters per second, you're just going to multiply by 0.2777. So I did this to 30 kilometers per hour, and this is my initial velocity in meters per second. I did it to 100 kilometers per hour, and that's 27.7 meters per second. And then here's the mass of my car. Well, since I don't have a force, and I don't have a distance, and I don't have any of that other stuff, I can go ahead and figure out how much kinetic energy my car had when it started. So I could just take 1/2 times the mass times its velocity, and that gives me the energy of my car when it starts. And if I take the final kinetic energy of my car, here's how much it had. So to get from this to that, we had to put that much energy into it. So that's how much energy was used. So let's go back to our power equals work divided by time formula here, or energy. So here's my final energy, here's my initial energy. The difference between those two would be how much energy was put in. Here's the time I used all that energy up. So if I take this minus that divided by 10, I get 41,904 joules per second. As I mentioned before here, a joule per second is a watt. So that's 41,904 joules per second, or 41,904 watts. If you stick around with me for just a couple more seconds, we'll go back to this 1 horsepower equals 746 watts. If I take this divided by 746, I find that that's 56 horsepower, which seems like a fairly reasonable answer for that car. And so that's a quick walk you through that problem to get to it.